This video is for topic 6.4, heat capacity and calorimetry. The objective for this topic is to calculate the heat, Q, absorbed or released by a system undergoing heating and cooling based on the amount of substance, the heat capacity, and the change in temperature. So this is where we're actually going to start calculating the amount of heat or energy that goes in or out of a system. So this all pertains to the first law of thermodynamics, which says that energy is conserved in all chemical and physical processes. So we're not looking at creating or destroying energy, we're looking at transferring energy. And when we study how energy is transferred, we call that calorimetry. These situations that we're looking at with this topic are specifically during heating and cooling processes. So when we're having a change in temperature. So the equation that we're going to use is Q equals M, which is our total mass, times C, which is the specific heat capacity, times delta T, which is the change in temperature. And your delta T is always going to be T final minus T initial. So it's always going to be your final temperature minus your initial temperature. If your final is smaller than your initial, so if your temperature went down, it's going to be a negative value. Remember, the sign of Q just tells you whether energy is going in or out of the system. So if you have a negative Q, you're showing that energy is leaving the system. If you have a positive Q, energy is entering the system. So there's really two types of C's that we can use. The first is the specific heat capacity, which is the amount of energy in joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. This means that the units are joules per gram times degrees Celsius. The specific heat capacity and the molar heat capacities are different for all different substances. The higher the heat capacity, whether it's specific or molar, the more energy you need to change the temperature. So the harder it is to change the temperature of that substance. The lower the heat capacity, the easier it is to change the temperature, or the less energy you need to change the temperature of that substance. Molar heat capacity is similar to specific heat capacity, except that it's the amount of energy, still in joules, needed to raise the temperature of 1 mole of a substance by 1 Kelvin. So molar heat capacity is using moles and kelvins, whereas specific heat capacity is using grams and degrees Celsius. So which constant you're going to use is going to depend on what the question asks and the units that you are given in the problem. When we look at a phase change diagram, the calculations Q equals MC delta T, some people refer to it as MCAT, because the delta, the triangle for delta, kind of looks like an A, so Q equals MCAT, is for only when we're changing temperatures. So that means we're not changing states. We either change temperature or state when we either gain or lose energy. Those changes don't happen at the same time. So these are the types of changes that we're looking at for changing temperature. So the states are staying the same. We're not going through any type of change in state using these types of calculations. The calculations for changing state we're going to look at next. But this equation, Q equals MCAT, is just used when there is a change in temperature. So that tells us how much energy we gain or lose when we either increase or decrease the temperature of a substance.